We're going to consider an example of a continuous time dynamic program. Okay, and this is something called LQ regularization or linear quadratic regularization. Okay, so the way the state is going to evolve is essentially going to be a linear combination of the current state and action chosen. Okay, and we're going to worry about minimizing some sort of quadratic cost. You think of a quadratic cost being sort of a distance between where we are and where we want to be. Okay, right. So let's give a kind of formal definition of that. And there are lots of ways we could kind of re-express this, but essentially the form of the problem we're going to try and solve is the following: that we have a continuous time dynamic program, okay, and the sets of states belong to some set of vectors in Rn, and the sets of actions belong to some vectors in Rm, okay? And the way the state is going to evolve, like I said, is that the change in the state is given by a linear function in the sets of current states plus a linear function which our control applies. Okay, so we can think that applies some sort of force, or we can think that sort of doing some repositioning and change of direction for the current state. Okay. Further, we look to minimize the cost, okay, which is given by essentially sort of xt q xt. So we're looking at some matrix q, and we're going to apply the state vector to either side of that matrix. We're going to assume that it's a symmetric positive definite matrix. So remember that a matrix is positive definite if when I apply some vector to it to either side, then it always gives me a non-zero answer. Okay, and symmetric means that if I take the transpose of the matrix, I just end up with the matrix itself again. Okay, essentially these sorts of matrices are the kind of things we use for distances. Okay, so if we use the identity function here, we'd end up with the sort of square of Euclidean distance. Okay, so we can kind of think of this symmetric positive definite matrix giving some sort of idea of distance away, maybe for some target. Okay, right. So these sorts of problems occur in all sorts of situations. So we've got some linear evolution. Okay, now lots of systems of differential equations can be approximated by some sort of linear approximation. So that's what this is doing. Okay, so even if the reality of your physical system isn't linear, locally it's often approximated by something linear like this, and so it's some valid up to some range. Okay, and then we're looking to kind of minimize some sort of distance function here. All right. Okay, so let's go about trying to solve this type of problem. So the first exercises essentially show that the HJB equation for a linear quadratic problem, okay, is given by the following. All right. So if we just scroll up, we'll just remember what our HJB equation is. Oh, can't scroll up. Let me get it here. Remember that our HJB equation here, okay, is that it's sort of the minimization of the instantaneous cost, and then we've got some partial derivatives here, the partial derivative of the loss function with respect to time, plus the plant equation that gives the state evolution, and that's dot producted with the partial derivatives of the state, and then if there's a discount, which there isn't in our case, we minus off the discount factor times the current value function. Though in our case we don't have a discount factor, so we don't need that. Okay, so let's just jump back to where we were. Okay, so to answer this question, we just need to remember the definition of the HJB equation. Okay, and that is that we minimize over the sets of actions, the cost being in state x and a. Okay, then we add on the partial derivatives of our optimal cost function. Then we add on f of t of x of a dotted with the partial derivative with respect to x of our value function, and then we minus off alpha, and there's no derivatives on the sky, x. Okay, so in our case, like I say, this is equal to 0 because we don't have any exponential decay in this guy. Okay, we could, but we don't in this specific case that we're considering. Okay, then we need to include what f is here. So f in our case is just this function here, a of x plus, I've used r, but this should be a b, typo. Okay, and then this maps exactly with this maps exactly with this, right? And then finally we need to include our instantaneous cost, which is exactly this guy here. Okay. Okay. So in other words, we recover exactly the same equation before, except for my typo here. Okay. All right. So we've got the HJB equation, and now, a bit like with the continuous time dynamic program, it's a bit like with normal dynamic programs, we need to go about solving this guy. All right. And what we're going to do is we're going to kind of take an educated guess of what the solution is. All right. So I guess you could solve a few of these by hand, get an idea what the form is, and then go about checking if this is the actual solution. Okay, so now we're going to guess that the solution of the HJB equation is of the following form, that the loss from time t onwards looks like this, that it's of the form xt lambda x. Okay, so again, we've got some symmetric matrix, okay, and we're applying x to either side of it, all right? So we can take a guess at that, and remember that if we find the optimal solution to the HJB equation, then it is the optimal solution overall. So we could take a guess with this, plug it into our HJB equation, right? Look what conditions that gives us on this symmetric matrix lambda, if indeed we can satisfy those conditions for optimality of the HJB equation, then we have found an optimal solution to the LQ problem, to this linear quadratic regularization problem. Okay? So, our job is to basically plug this in to our HJB equation, okay? And then what we're asked to do is argue that the HJB equation is minimized by an action of the following form. Okay, so we'll check that in a moment. And thus, for the minimum of the HJB equation, so remember we need that the minimum of this over the set of actions to be 0, okay, so when we minimize this over A, then we require the following condition, okay? All right, so let's go about doing that then. All right, so this requires a little bit of work, but not too much. Oops, let me just get my pen back. All right, so answer to this guy. All right, so we said that L of t of x, x of t, tx is our form of the solution in our HJB equation up here. All right, so what do we need? We need essentially to get this partial derivative here and this partial derivative there. All right, so we need to do the partial derivative with respect to time and then the partial derivatives with respect to x, the space component. All right, so, well, you can check that differentiation for each x is going to follow in a very similar way to it normally does. So this is sort of x times a constant times x. Okay, so if I was going to differentiate something that's sort of x squared times a constant, I'd end up with sort of 2 lots of that times x. Okay, so you can check this either by directly checking how is the component by component, or you can check that if I differentiated with respect to each term in this vector, then I'd end up with each term corresponding to this kind of matrix multiplication here. All right. Further, I can differentiate it with respect to time. Okay, so assuming that this function lambda of t is differentiable, I'm going to end up with the derivative of just each component of this matrix. Okay, so lambda dot of t of x, where lambda dot means the derivative of each component of this matrix. Okay, right, so that's fine. So now we need to plug in these values into our HJB equation, which is just above. Okay, so we need to plug in the partial derivatives here and the partial derivatives there. Okay, so if we do that, so substituting into the HJB equation gives the following, that again we need to find the minimum over the sets of actions that are available to us. Okay, and we're going to minimize the cost function as before. Okay, and then we need the partial derivative with respect to t, okay, which is, so I have it here, this. And then I need the partial derivative with respect to x multiplied by the Plant equation. Okay, so then I'm going to have the Plant equation multiplied by 2 lots of lambda t of x. Okay. All right. So now I've got to a point where I have written down the HJB equation, given that the form of the solution looks like this. All right. Now I might want to minimize this over the sets of actions. Right. And essentially we've got something that's sort of got a quadratic term in A and a linear term in A. All right. So it's a little bit like minimizing a quadratic function. So we've got a function that looks sort of, let's use some constant, sort of c of a plus d squared plus a plus some other constant e. So we've got, a term that looks a bit like this, right? We need to minimize it at the bottom, okay, of this quadratic function, right? So we can do that essentially by differentiating, right? So let's do that. So we just need to differentiate now this with respect to a and set the derivative equal to 0, just like we would do it in normal calculus, right? So differentiating with respect to the actions a, we get, well, just like before, we're going to get a bit like we got 2 lambda x here, and we differentiated here, so we're going to get, well, 2 RA here, right? The derivative of this with respect to A is 0, okay? The derivative of this with respect to A is 2RA. The derivative of this with respect to A is 0. The derivative of this with respect to A, we're going to pick up 2 lots of x of t transpose lambda t, okay, and then this is going to be applying BA. Okay, so notice I've just kind of swapped the signs over here. Okay, so that's the derivative of this with respect to the sets of actions. Now we need to set those equal to 0. Right? So that's sort of the same as saying that the derivative at this point in this quadratic curve is 0. So we've got the derivative here. Right? And this is giving the value of a for which the derivative is equal to 0. Right? Okay, so notice that I can now solve for a. Oh, I'm forgetting, I've written down a here. I've differentiated with respect to a, so I need, that shouldn't be there, my mistake. Okay, so differentiated with respect to a, I can now solve for a. In other words, I divide by 2. I'm going to assume that this is, since it's a positive symmetric matrix, that means that it's actually invertible. Okay, so I can then take r to the minus 1 on this side. Okay, so I'm going to get that a is equal to minus r to the minus 1, so it's inverse b transpose lambda t. So I'll sort of move this over to this side. Okay, taking the transpose, which doesn't affect anything here. okay, and then I've taken r to the minus 1. All right? Okay, so that's enough to say that the derivative is 0, and this is the condition for being the minimum of this function. But we need the minimum, sorry, to be the condition to be the minimizer of this function, but we need the minimum to be equal to 0. Okay, so we need to substitute this back in and then add the condition. This is going to need to be 0. All right? So, substituting this back into this expression, notice what we're going to need. So we're going to need this with the a substituted in from here, back in here, to be equal to 0. So I need 0 equal to xtqx plus ATRA. Okay, so that's going to give me from this AT lambda T B r to the minus 1 times r to the minus 1. So it's going to give me overall an r to the minus 1 in here. All right, times bt lambda t of x. Okay, I think that's right. All right, that's a bit messy here. Then I'm going to get this condition from over here. So x transpose lambda dot of t of x. Right. Now we've got this guy. All right, so it's going to get a little bit tricky. Okay, so I've got, let me just double check that I get this right. Well, in fact, I'm just going to write down the answer. I'm going to leave you to check it when you get home. But what you should get out of this is, okay, so out of this you should get lambda t of a plus a t of lambda t. Okay. All right. And I think there's a slight typo in here. I think I've got this q shouldn't be there, so that's a typo. All right, I'll double check that and make sure the notes are correct. Okay. So anyway, this will arrive at a condition of this form. Oh, I need to make sure I've got my x's involved here. So I should have an x transpose and an x, and an x transpose and an x. Right. Okay, so all of this together will give me this condition up here. All right. So in other words, this is the condition for being the minimizer, and the condition for the minimizer being equal to 0 is this condition. All right, which you can notice is essentially a differential equation in lambda of t. Okay, so in other words, if we wanted this to have a minimum of 0, I'd need probably each component of this matrix to be equal to 0. Okay, so that leads us to the next part of this question. So show that the HJB equation to be satisfied, then it is sufficient to show that this is true. Okay, so the answer to that is to note that this implies that this term that star above in 71 is 0. Okay, and further, and the condition lambda t equals q of t guarantees that the optimal solution L of t of x is equal to x qt x. Okay, so from the termination condition of the HJB equation. Okay, so essentially, if I want this to hold, then I need this to hold. And one way to make this equal to 0 is to make this term inside the square brackets equal to 0. And that is exactly this condition over here. All right. Now this is a special sort of condition. It's called a special set of equations, and it's called the Riccati equation. Okay. Notice there's a differential equation that you have a termination condition with, and then you can solve that differential equation backwards, okay, numerically or otherwise, in order to give you the optimal value function, okay? So the differential equation here above is called the Riccati equation, okay, and it says to argue that the solution of the Riccati equation is optimal for the LQ problem, okay? So, well, this final step is not too bad, because if the Riccati equation is solved, then, okay, then L of t of x equal x lambda t x solves the HJB equation with actions given by the above expression here. Let's just copy that. So with actions given by this. Oops. Just delete that gap. Okay. And so if we have a solution to the HJB equation, then we have it's an optimal solution. So by our previous exercise, okay, so let's just get the actual exercise itself. So it was this exercise at the bottom here, exercise 68 on the optimality of the HJB equation, which said if we can find a value function that solves the HJB equation, then it's optimal. Okay, so by exercise 68, L of t of x is optimal for the HJ is optimal. Don't need to say that. Okay, and that's it. Okay, so that gives one idea of how to go about solving one of these continuous time dynamic programs. Okay, so notice we took a guess at the solution. Okay, we wrote down the HJB equation, we took a guess at the solution to the HJB equation. From that we derived some conditions for that form to be the optimal solution. Okay, in this specific case it gave a differential equation. So whenever we can solve this differential equation, which is in principle solvable, it's not too difficult to form, okay, then we have the optimal control for that system. Okay, further, from the way we solved it, it also gave us the optimal action given each state and time. Okay, so we can completely solve the system by solving this differential equation backwards from time capital T to time 0. Okay, all right, and that's a very common form of solution. Okay, a very related form of optimal control is called a Kalman filter, which follows a very similar form with some randomness in it, and that was, for example, used for the moon landing and other types of control problems. Okay, so there are many systems that use this kind of LQR theory. Okay, great. Okay, now that's enough on the kind of discrete time, the deterministic control setting. Next we want to move more to diffusion processes, because obviously we want to work on financial applications, and so we want to be considering the kind of stochastic analog of this continuous time dynamic programming. So I'll start to set up that in a minute. Before I do that, I'll kind of recall some of the literature that you've learned on stochastic integration. Of course, you've covered that in your stochastic calculus course, but it doesn't hurt to recap, because the kinds of Taylor expansions that we're doing to define the HJB equation will need from stochastic integration to do it in the random case. Okay? All right, so we'll cover that next time, and then we'll move on to diffusion control. Okay, thanks.